as Eric already pointed out, the purpose was to make like a general test system, which is at the moment was tested by the X-FAB chip, but there is no obstacle to use it with any kind of test chips what you will ever made, and we will also prepare it soon with the AMS chip, or sorry, is it TSMC? Alex, is it AMS or AMS, right? Yeah. So it will be also prepared for the AMS chip. So in general, as what concerns the physical capabilities. So here comes the. You see my cursor, by the way? You do, okay.
Yeah, we
So
can see
here
that,
here comes
Heidi.
here
Thanks.
comes the this test chip itself. So the test system has 4 analog input channels. Through which it can read analog data from the test chip, then 16 analog output channels, which can actuate different inputs of the test chip. It contains of a picoamp source meter and a relay board. So all these peripherals together, the test system could uh, control simultaneously. And here are some screenshots of the test system, but I will go into details right now. So shortly, I will introduce the software components, the software modules of the test system. So as you can see, it is organized in a tabbed graphical user interface. The first page is the project page. This is what you can see here. You can give what are the files which holds the different settings of the project, and also the folder where the data is stored and generated. Then there is a variable manager. So here we use those variables to allow the automated control of the measurement tasks. I will show you examples, but just to understand what I'm talking about here. So there are 2 kinds of variables, loop variables and so-called formula variables. For instance, here this G is a loop variable which runs from 0 to 5. And here is this other variable CG, which contains a formula which refers back to G. So this CG volt inv is a variable which runs from 1 to 0.2. You can see here, so when G is 0, then this variable is 1, and as it runs from 0 to 4, then this variable will go from 1 to 0.2. Okay, so there is an interdependency between those variables, and I will show later how those variables can be used to automate your measurement sequence. Just keep in mind that we have those variables. Then we have the task manager. So in task manager, there are tasks and there are actions. Each task contains 1 or more actions. Okay, so there is a hierarchy here. The task is the higher level and the task may have actions. Then you will see that there is a higher level in this architecture, which is the workflow. A workflow contains of tasks. So, for instance, here, the task is called set CG sweep, but the name doesn't matter really. What you can define in tasks are actions. What kind of actions do we have implemented at the moment? You can define a constant voltage action. This will generate a constant voltage on one of the analog output channels. Then you can define several analog outputs at the same time. This is what we call a voltage array task. Then you can define voltage pulses. This was a wish of Philip, that we can generate also pulses on the defined analog output channel. So these were related to the analog outputs. Then there is one task which is related to the analog input. So with the voltage reader task, you can set up conditions to read data from the analog input channels. Then we have the source meter action, which defines a measurement task for the source meter hardware, and one for the relay board. This will actuate the different relays of the relay board. So those action types can be combined freely in a single task. And as an example here, so this is the task name, set CG sweep inv. It has three actions, one which is related to the relay board, and then two which are constant voltage tasks. So here now we are editing a constant voltage task. So how can you do this? Here you select which analog output port you want to apply the constant voltage task to. So here you can see that those are already the port namings of your design, Philip and Stefan. Okay, so there is a like a dictionary between the physical channels and the daughter board. This can be chosen in the project page. So for instance, here, this is XFAB-DB01. This is XFAB daughter board 01. And then there is a list of different daughter boards which are tailor-made for the different measurement tasks. So for instance, here, this CG12 is the control gate of device 12, CG13 is the control gate of device 13, and so on. So the user selects this port, then one can set the voltage level to be applied as a control gate voltage, or one can use a variable. Remember the variables what I just showed in the last slide. So in this case, the voltage level of CG12 will be controlled by this variable. So remember, this variable was controlled also by the loop variable G. If this sounds to be overcomplicated at the moment, soon you will understand when I will show the workflow. Okay, and also those tasks can be tested in situ by pressing this test button here. There is another example for an action. This is the voltage pulse. So here you can set up all the parameters of the voltage pulse. So this 100 millisecond pulse will be applied on the tunneling gate 12, but the same like you can apply this pulse on tunneling input 13, and so on. And also the parameters of these pulses can be also controlled by variables. Or a third example, here you can set up the parameters of the source meter. So you can define what would be the source, what you want to measure with the source meter, and how many samples you want to average. Or for the relays, you can select which channels of the relay board are activated, and so on. Okay, so it all makes perfect sense. Then the next module of the test bench software is the workflow. So in the workflow manager, the task sets, remember, task sets contains the actions. So this task sets could be called in a predefined sequence or in embedded loops. So I will go into the details now, and will explain you what are the elements of this workflow. This is an example, but will help you to to understand how does it work. So this workflow starts with the clean up task. This clean up task resets all the ports and sets to 0 volt. Then power up will provide the VDD or PVDD for the test circuit. Then the bias task will set the P bias values of the selected amplifiers or transistors. Then the breakpoint is a special element of the workflow. It interrupts the workflow and waits for an user feedback or a user interrupt, a user interaction. So for instance, here, after powering up and biasing the circuit, there is a chance to measure what is the actual value of the output of the amplifier, or you can check the current consumption of the circuit and so on. Wait element is an intentional break of the workflow for a given time. In this case, this is 1 sec. Then we start reading, start collecting the samples from the selected channels. Then what comes here is a loop. This loop is controlled by the G loop variables. So between repeat G and next G, this section will be repeated 5 times. As you can see, this loop contains the set CG sweep task. This will, in each loop iteration, increase the CG control gate voltage by 0.2 volts. You can see here why 0.2, because this CG volt variable is controlled by the G variable, and its value is the 0.2 times the value of the G. So it runs from 0 to 1 volt. Then it contains 2 internal loops, which sweeps up the tunneling voltage from 0 to 1 volt, then back from 1 volt to 0 volt. Okay, so we have 2 loops here. This task is controlled by the tune volt variable, which runs from 0 to 1, and this other one runs from 1 to 0. So what will happen here? The tunneling voltage will go up from 0 to 1 volt, then back from 1 volt to 0 volt. And this is embedded in this first loop. So the control gate and the tunneling voltage will be applied at the same time. So the CG will be increased, and in each iteration, the tunneling voltage will be also updated. But I will show you the graphs soon. Okay, and at the end, we have this parking task, which resets all the ports and releases the PVDD voltage from the test circuit. So let's see a demo. In this demo, we were testing device 12 and device 13. So those are the devices which contains of the tunneling gate and control gate, and they have this simple amplifier with a biasing option, and therefore the output is a voltage. So here we control the CG, control the tunneling, control the bias, and reading a voltage at the output of the amplifier. And we will do the same testing simultaneously for device 12 and device 13, which are similar in their topology, but they have a different size of tunneling gates. So here you can see that these port names, CG12, CG13, D-Sense, P-bias, and so on, those are assigned to actual physical ports. This should be only once, because when you are using the daughter boards, those are already predefined. Okay, so you can take this as a given. Also, for each port, a voltage range can be set, and if the voltage what the user intends to set up exceeds this range, either higher or lower, then the graphical user interface warns the user that the limits were exceeded. So this is how the measurement configuration looks like physically. You can see that at the moment we are using these cables because the daughter boards are not yet ready. But when the daughter boards are ready, then all those cables will be replaced by this adapter board and the wire cable. Then it will look like much clearer. Okay, so once again, this is what we do. The control gate voltage is increased during the measurement from 0 to 0.8 volts. And in each iteration, the tunneling voltage is going up from 0 to 0.9, more precisely to 1, then go back from 1 to 0. Okay, and this is done for each iteration. And let's see. Yeah, sorry. So in the workflow, this is how it is implemented. Then let's see some video so you can see how does it work in action. So here you can open the project file which contains all the settings. Also, you can define a data output folder in which the measurement results are collected. You need to select the necessary daughter board, which is DB01 in this case. Then you open the project. Here you can set up the different variables. Here you can set up the different tasks. For instance, this is the cleanup task in which we set up different voltages for the inputs. Then there is the power up task when we set up the 2.7 volts for the PVDD. Or here we have this CG sweep task, which sets up the CG voltage of CG12 and CG13 inputs, or this sparking task, which will reset the voltages or on all voltage outputs. Then here we have the workflow. I already explained what is the content of this workflow, and you just execute the workflow by pressing this play button. Here was the breakpoint when you can check, for instance, if the PVDD voltage is there. Then after waiting, the workflow just starts. So this is how it happens in an automated manner. So that was it. In total, 100 measurements were done. And then in the project folder, you can save the data and check it. So there is a viewer application for the measurement data. Here you can see that all the measurement channels are stored in a separate titles here, and there you can see the voltage outputs. I will show you the result more precisely, but here I just wanted to show that everything what basically happened during the measurement sequence is stored here and can be displayed here with the necessary timestamps and so on. Also, all the data is exported then to Excel, so you can or in CSV. So basically, you can then process the data in MATLAB if you want. Okay, so this was the result of the measurements. So once again, in each steps, the control gate voltage was set from 0 to 0.8 volts. And in each iteration, the tunneling voltage was set from 0 to 1, then from 1 to 0 volts. And as you can see, when the CG voltage is smaller, then the tunneling voltage has a greater effect on the output. And as you increase the CG voltage, then the tunneling voltage has less and less effect. I'm not saying that this measurement is meaningful, but at least it shows that the two devices could be tested in a simultaneous way, and then it works as expected. So then
short interrupt.
Yeah.
I really have to leave like now precisely, right? So because I have to prepare for 5 minutes for the
Sweet child is this 12 and 13, and it was already demonstrated. So now comes the other. I think the next one is Stefan's. So here, what we have done. Alex, can you confirm that those are Stefan's ISFETs already? Yeah. So here is your device, Stefan. So what we do here is to measure 3 independent ISFETs on the same chip, simultaneously from the measurement sequence point of view, but they were measured sequentially. By using a single source meter, and selecting the device was done by the relay board. So here the measurement system controls the relay board to select the device, the source meter to measure drain current, and the gate of each devices were biased by the compact duct. So here really all modalities of the test system were used.
Yeah, just ask questions. Or do you want to have questions at the end?
Yeah, okay. Then let's see what sort of variables.
Ference, Stefan asked if he could interrupt with some questions during presentation. Can you do that?
I can wait until the end as well. I just
As you wish.
Okay, you want to wait to the end. Okay, that's fine. Then,
wait till the end. Yeah, yes, of course.
Okay, cheers.
Of course.
So here we are using variables. One for controlling the relays. The other is for biasing the ISFET gates. Then there are different tasks, but probably the most relevant one is this test ISFET task, which contains of 5 actions. The first action is to switch the channel on the relay board, then set up the bias for the 3 transistors. So these are the gate voltages. And then finally to make the measurement with the source meter. Here the drain source voltage of the ISFET is set by the source meter, and the drain current is measured. So this is then the test ISFET task. And on the workflow, you can see that there is a cleanup, a power up. Again, it has the same purpose as in the previous workflow. Then there is a breakpoint, also the same purpose to check whether the voltages, the work points are set as intended. And then this external loop, relay loop, will switch the channels, and then the internal loop, the ISFET loop, will set up 10 different gate voltages for the tested ISFETs. If I go back here, then you can see that this will mean voltages from 0 to 2.7 volts exactly within this loop. Then let's see, this is the result. So drain current for transistor 1, transistor 2, and transistor 3. So from this, we can say that those 3 transistors behave pretty much the same manner. Then third demo is concerning the photodiodes on the XFAB chip. So we measured here 2 devices using a similar setup, using the relay board to select the device, and the source meter was used to measure the cathode current in this case. And then the measurement sequence consists of 3 parts, or 3 cases. The first is a dark case when the lid of the chip was closed. Then in the room light case, the lid was opened, and then the photodiodes were excited by the actual room light. And in the third case, also a torch was used, and what we expected, that in this case there will be a higher photocurrent. So just showing you the measurement sequence here, we didn't use loops because those are 3 like different measurement setups, so to say. The 3 measurement cases are divided by the 3 breakpoints, and here the user is prompted by a message that dark mode, so the user knows that the lid should be closed, the light mode, the lid should be opened, torch, the torch should be turned on, and so on. So at those breakpoints, the operator has some time to prepare or modify the measurement setup. And what happened within the different cases, this photo sensor test 01 and 02, those are relay commands, so they will select the necessary channels, and current measurement is always the same task. It is what it is, so it measures the photo current. Also, this workflow is framed by a clean up, a power up task. So this power up will apply the PVDD voltage, and Park will release all output voltages and set back to 0. Let's see the results. So here you can see the photo current reading from the 2 photodiodes. So when the lid is closed, then it is basically not. If you zoom in, you can see some noise in the femp to amp range. So there is nothing basically. Then when the lid was opened with the room light, then in case of the first diode, there was some measurable photo current on the E-8 range. And also, if you zoom in, you can see some reading on D2 photodiode close to the noise floor. And when the torch was also applied, then the photocurrent increased definitely. And also for D2 photodiode, there is a much higher current. if you go further into the analysis, the ratio of increasing this current of D1 is similar to the increment of D2. So as a summary, the functional testing was completed, and all the specified functions were verified and working as expected. The source code is delivered for the guys at USN. Just for your information, the software was implemented in Glang. This is the name of the programming language in object-oriented programming. The whole program language is called GOOP, and the implementation was in LabVIEW 2024. So meaning that GOOP is an open programming language, but the only implementation per day is in LabVIEW. Anyway, executables of the software code are available for Windows x64, so there is no LabVIEW needed for running the codes. It was compiled for Windows systems. The port libraries are available for the XFAB chips, but I will help Alex to prepare the port libraries for the AMS chips as well. And there will be one daughter board reference design available for the XFAB setup, and hopefully then Alex will be able to prepare the remaining daughter board designs. So this is what we have. And I think we have time for questions also.